Hello, I am Ismail from UniKL PY, British Mission Institute. Okay, today I will talk about the project development. This is still under the introduction to ARM and the basic of microcontroller programming. Okay, so we talk about project developments. I will show the example of project developments, and based on the further, I com- uh, I I also include share the references for you for further reading. Right. All right. So first of all, what is a project development? Project development actually is just uh, the steps in validate the the development process up to verify the complete system. Okay. So the first step that we have is define state, then go to the design step, then go to the build and test prototype, then go to the software development and system integrations. Finally, the final, what we call as system test. And if you see here, this step for the design a bit wider because of what's saying by lot of authors, especially Bibre, saying that the more you spend in designing the project, the less it takes to complete the projects. So, as introductions, and so this is uh, the good what's practical is to spend more time in designing the project, right? Rather than you go to build the and test the prototype or writing the software without knowing, right? Without knowing what is your planning and what is your objective. All right. So actually, in quality, when we talk about quality, actually the project development is in control and finally assurance and assure. So verify, validate, and verify. So that two terms, two uh, concept or words that we use in project development. So if we go to the defined steps, right? First of all, we need to ask why. Right? So actually definitions, sometimes called definition stage. Stage is to implicitly confirm the project's peaceful and success. This stage focus on evaluating its practicality and ensuring that it can indeed be completed. So how to conduct it? Clearly outline the specific function and task the device is designed to perform. And for example, later we will talk about the humidity and temperature display. Provide detailed specification that thoroughly describe the project intended operations and functionality. Actually, this is what we call as the final test later. Right? Include an anticipated budget, a list of required resources, and a comprehensive time plan for the project's executions. So only these three actually. One, clearly outline specific functions, provide detailed specifications, and include anticipated budget, list of required resources, and comprehensive time plan for the project executions. So the result is a micro level block diagram which provide an overview of the circuit that will constitute the project, which ensure that the project design is feasible and will functions as intended. So uh, if you submit your projects and to the customer, maybe to your superior or to your lecturer, whatever, right? By looking at the macro level block diagram, they can guess whether the project is feasible or not, right? And then complete set of specifications, electrical functional specification, which provide detailed information about the electrical and functional characteristics of the system. So the voltage supply, the current required, right? The output, how it's look like, right? The display, the format of the display, and the lowest temperature that it can work at, and the highest frequency, for example, that it can detect, and so on, right? And operating specification align the personal detail, including human interface and user interaction. So sometimes we need to provide this, especially for the project such, for example, you are designing say uh, the what right? Mm, this the configurable, right? The dynamic configurable serial port, for example, right? So you must provide them, right, the user with the what's the personal details and the human interface. Maybe you have some sort like, you have some sort like storyboard, right, for your project and so on. So they should know it, how to use it. And then another result could be the project proposal, right? Sometimes we call it the project feasibility, feasibility reports, and then we call it project proposal or feasibility reports, which outline the project concept and objective. So inside it we have definition phase summary, provide a concise summary of the initial planning, the problem definition phase, and of course it come with the objective, and then it come with the scope, limitation, and so on. Research and feasibility testing summary highlight the finding from research and feasibility studies, which usually we when we conduct the feasibility studies, we we can see that, okay, from the scope and the limitations, right? We we can see that either the project is feasible or not. Written specifications include a detailed list of system specifications. Anticipated budget provide an estimate of the total cost involved in the project, and the completion schedule or timeline, right? Which present a timeline for the project's key milestone and final delivery. So this demonstrates how the investment leads to a successful and a practical outcome. So from this project proposal, uh, I do myself sometimes right, submit the project proposal, but rejected because of, you know because of maybe the project proposal that I submit are not, right, are not what feasible for the reader, right, for the reader or customer. So not this is also known as a feasibility study, right? Okay, so the definitions stage, also known as a feasibility studies. Sometimes we heard people say, okay, please conduct the feasibility study before you carry on with your project. So the feasibility study is the definition stage, right? Definition stage, or we can sometimes we call define stage. The second one that we have is design. The most important, I say, right? So what's actually design stage to populate the micro block with the actual circuit design. So we have a micro block diagram shape, a micro level block diagram. Then we will populate the micro block with the actual circuit design, right? Mm, and sometimes we simulate, right? Simulate it using the any software, right? Develop a detailed flowchart or software outline to define the project software structures. So this is what activities that done in conduct in the design stage. So we have hardware stage design steps, which provide detailed description of micro block outline during the definition phase. Conduct comprehensive research on the component and circuit relevant to each block. Design a preliminary circuit schematic for each block. Develop a complete overall schematic integrating all the blocks for the project. So while you design the preliminary circuit schematic for each block, please simulate it. Please simulate it to or find out from the Google out there for the correct circuit and prove it, right, by submit. And next we have the software design steps. Enumerate all the tasks that the software needs to accomplish. Identify and prioritize tasks that require interrupt-based handling. Develop a software flowchart or outline specifically for each interrupt-driven functions. And then create a software flowchart or outline for all other tasks related to the project. So we develop a software flowchart outline specifically for each interrupt-driven function. Create a software flowchart or outline for all other tasks related to the project. So the result that we have later on, a detail of preliminary block diagram, a comprehensive set of circuit schematic, a creation of software flowchart or outlines, and a list of intermediate tests to validate the progress. So in the first part or first stage, we have the final test, right? Final test, which is we call as the specifications, project specifications sometimes. And then the second one, we have the uh, intermediate test. Intermediate test is the test that will be conducted for each of the subblock, right? But the functional or the specifications or the final test, right? Actually, the test that we conduct to test the system, right? So that is different. Okay, next we go to the build and test prototype. So why we conduct this stage is to ensure the correct input signal is provided to the controller. Yeah, yeah. The controller can what accept low voltage TTL 3.3 volt. So ensure that the voltage is at 3.3 volt, for example. Right. The input to the analog channel should be not more than 3.3 volt, right? So we need to ensure that. Oh, the input to the analog channel, which is to volt equal to 200 volt. That's all, right? You need to ensure. Verify the controller output drive the output circuitry as expected. This is another thing we need to look at, right? So in terms of the outputs, we also need to look at these things as, for example, we drive the motor, right? Maybe we need to use the MOSFET. Maybe we need to use the low to high voltage, right? Interface say the IR2110, for example, right? Thereby isolating or attributing any issues to the software. So later, if we have a problem, we cannot say I don't know. Yesterday's works, but now it's not works, right? So we can burden everything to software, right? So anything we blame software, no more hardware, because we have conduct the build and test prototype process or stage. How? Construct and test the circuit. So assemble circuits, including all subblock, test each subblock individually, right? Against what? Again, the intermediate test previously that we have seen. To ensuring it meets the functional requirements, right, specified. And then, whenever possible, utilize actual inputs and output devices. But if there is no input and output devices, such, for example, you are ordering something from Ukraine or Russia, right? So it takes maybe 3 months to come, but it just like the voltage generates a voltage, so you can use maybe the analog the preset or variables, right, to simulate the inputs, for example, right? Maybe you order maybe the special LED, right? Just switch on just like on when you apply a voltage. So maybe you can use the simple LED that we have, right? What the regular LED that we have. Use simulated input only when necessary, right? When necessary. If not necessary, use the actual input or and output. And then result, validated functional hardware prototype. This is what I say. If we validate that the hardware is functional, right? Then anything later blame to the software, not the hardware. Alright, software development and system integration. So what actually this stage is developing and testing the software to ensure it meets the project specifications. So how? So writing and testing the software, we utilize simple function to test the functionality of each input and output device. Test each function individually to ensure proper operations. Right? Test each functions individually. So we should know how to test the functions. Right? Then develop the overall software in a step manner. Step-by-step manner. Okay. The testing here still the intermediate test that we develop in the design, right? In the design stage. Alright. Then after that, then we combine all that software together, which we call as system integration. Remember, it must be conducted in a step-by-step manner. Alright. It looks stupid, but actually this is the brilliant way of what completing your project. The development process can follow either a top-down or bottom-up approach. Top-down and bottom-up approach depending on the project's requirement and the debugging tools available. So it depends. For example, if you have a serial port or USAT, right? You can monitor the project using that software. So I suggest you use top down. But if you don't have it, you have the LED or buzzer as a then do it from bottom up. Do using bottom up approach. So a result is fully functional project utilizing either real or simulated input and output devices. So finally we have the system test. Right? Why? To gain customer approval. Right? Your supervisor, your boss, your superior, whatever. And how? Deploy the project for use, conduct a demonstrations for the customer, and verify its functionality to confirm compliance with the finalized or final specifications. So the result is a fully working project. Trade to banner at all because a lot of the information here I got from these books, right? You can read the books. I provide the references and the back later for you. Okay, next we do real-time environmental monitoring system for temperature and humidity display. So as introductions, right? The real-time environmental monitoring system for temperature and humidity is an embedded project designed to deliver continuous real-time updates and environmental conditions. So this is the definitions of the project actually. Right? Utilizing a temperature and humidity sensor, the system collect data at 100 millisecond interval and display the information on a 2x16 LCD screen, and a lot the first line of the display show temperature, where the second line show humidity, ensuring clear and concise monitoring. The accompanying block diagram illustrate the system architecture. Yeah, and a detailed flowchart is provided. Right? This is a detailed flowchart provided in the following slide. Key project components. Okay, I show you the flowchart. So the flowchart is very simple. Just start system initializations, right? What is system initialization? Configure the system clock, initialize peripheral, GPIO, initialize the DHT11 sensor, for example. We use DHT11 for that. Then initialize the I2C LCD. Then after that, we wait for the time out. If the time out, then read temperature and humidity from the HT11. Then after that, format the data for LCD. Right? Format the data for the LCD display. This is responsibility. The first row show the temperature reading. The second row display the humidity reading. And time out implementation introduces strict time out intervals such as 2 seconds, which is appropriate for this project to ensure periodic updates. Right. So update the LCD and then wait and sleep again. And wait for 2 seconds. Then read temperature and then format it for the LCD display and update the LCD and sleep again. Right, that's the project. Right, the flowchart of the project. Then the key project component including configuring a time force periodic sensor reading, integrating the sensor with the microcontroller, and formatting the data for optimal presentations on the LCD. The objective is to create a reliable, responsive, and user-friendly solution tailored to real-time environment to monitoring across diverse applications. The functional specifications are outlined below. So the functional specification is data update rate, display update. For example, here every 100 milliseconds. LCD display layout, line 1 display temperature in the format of temperature, temp, double dot, XX degree Celsius. Line 2 display humidity in the format hum, double dot, XX%. And then timer communication, timer is set to trigger the data read and display update every 100 milliseconds. This example of the defined stage. And another thing here, we have the flowchart of the project, the project milestone, right? The project milestones or the time plan. So it's showing the detail of the project activities. For example, project setup, initialization of the communications, display integrations, this testing and debugging, time out and optimization, documentation and refinement, project reports and presentation, final review and submissions, final limitation and presentation. So here we show the start and end of each activities. Each activity, we need to show the start and end. Right. Alright. So this is a project milestone. The second one that we have is the cost estimations. So cost estimation just list down the components used, the quantity required, the approximate cost, and the total cost. And normally, we multiply 10% for the miscellaneous. So, for example, here we have we can put it as 2,000, for example, 200 ringgit. And this project is pretty cheap, because we use the Nucleo 2 times 16 LCD display, I2C base, temperature and humidity sensor, right? Very cheap actually. Example, DST22. DST22 cheaper than DST11 if I'm not mistaken, right? Then we have resistor and capacitor, jumper wires, breadboard or PCB for prototyping. I think we can use tripod and power supply, example USB or 5-volt adapter, for example. Okay, this is a tentative block diagram. Okay, tentative block diagram. Compare it to the block diagram here. This is the tentative block diagram. So we show here the connections, the ground, plus 5 volts, PB10, PB9 connect to SDA and CL, and then PB0 and data line for the DHT. I think this one is DHT22. This one is more expensive, yeah. The white color more expensive than the blue color. You can read about DHT11 and DHT22. Actually, both them sensor for temperature and humidity. but with different cost, price, and different specifications, right? All right. Then in the design stage, we list down all the software required, right? So we have software in a slide system, read temperature, read humidity, display data, update timer, right? Process sensor data, and then hardware microcontroller board. We need a Nucleo, for example, Nucleo F401RE, temperature humidity sensor DST22, for example, I2C base 21011 LCD display, and then power supply 9 to 15 volt power supply with DC jack, female 2.1 connector or screw terminal block. Okay, this one is a screw terminal block, right? Connect it to the adapter, convert it to the wire, so we can connect the wire here to be in here. I think we have be in here and ground here. All right. Software hardware intermediate test. So how to test it, right? So we list down them, then we need to know how to test them, right? Because we're going to do that intermediate test later on during the software software development and integrations, right? Next, we need to have the intermediate test for the hardware. Power initialization, verify power up, sensor accuracy, update interval, display format, real-time response, continuous operation, and power consumption. But it's not likely correct in this one, okay? Then build and test prototype stage. Integrating and testing the hardware component with the microcontroller. So this involves integrating hardware components with the microcontroller, ensuring their functionality through systematic testing. Below are the key steps undertaken. First, LCD integration and testing. Begin by connecting the 2x16 LCD to the microcontroller, ensuring power writing for that proper writing for data, control signal and power, upload the run a basic LCD driver code to verify the connection and functionality. This test confirms that the LCD initialized correctly, display characters as intended, and respond to command from the microcontroller. Any issues such as incorrect wiring or instance error are identified and resolved during this stage. Second one, we connect the DST11 sensor to the microcontroller, and then connect the after and then ensuring proper alignment of data, power, and ground pin. Upload the execute the basic DST sensor code to verify communication between the sensor and the microcontroller. And then this step ensures the sensor accurately reads and transmits temperature and humidity data to the controller. Troubleshooting occurs if the sensor fails to provide expected outputs such as incorrect data formatting or communication error. So this preliminary test establishes a correct integration and operation of LCD and DST11 sensor, forming a solid foundation for further development. Right? So we address and resolve the potential connectivity or functionality issue early. So the system reliability and performance are enhanced. And then we do the software development and system integrations. So we have two things. I2C based 2x16 LCD, right? And the other one we have the DST11. So for the 2x16 LCD, maybe we need the microsecond delay functions, create a precise delay using time configured in time-based mode to accurate timing control. Busy line check functions, monitor the busy flag of the LCD to ensure readiness for sending command of data. Command sending functions, send specific commands to the LCD for configuration or operation. Data writing function, write individual data bytes to the LCD for display purpose. So from that, then we can develop another functions to send string or string writing functions outputs a complete string to the LCD, display it on the screen. And then LCD initialization function. This is the most important thing. If you cannot initialize the LCD, then you cannot do anything. Configures and initialize a 2x16 LCD for operation, ensuring proper setup. Cursor positioning functions, to format the display later, you need to move your cursor. So position the cursor to a specific row and column on the LCD. Finally, display clearing function, clear the LCD screen when needed to prepare for new data or message. Maybe you want to write something, then you can you need to clear the previous data or display on the LCD. So you need this display clearing function. For the DST11, you need of course, DST11 initializations and DST port and ping to the user specific setting and activates timer X in the time-based mode, because you're going to use that time X for your microsecond delay functions, because DST11 require very precise time delay, very precise. So for that reason, we need to design that time delay, microsecond time delay, using the timer. Data line configuration functions configure the DST11 data line as either input or output depending on the operation. Because DST11 is one example of one wire communication. So that wire can be input, that wire also can be output. That wire send the command, that wire read the data from. Trigger start conditions, send the necessary start signal to the DST11. We need to wake up the DST11 before we can communicate with it. So we need to trigger it. So I call it as trigger start condition. And then when we trigger the DST11, it will respond. So we need to check either it is respond correctly or not. If not respond, it can be maybe the wire broken, or it can be the DST11 is not there. Not at that line, data line, for example. And then data validation function, read temperature and humidity. So the data 64 complete. The data is 16 52 plus 48. Data is 48 bits, which is the lower temperature, high temperature, 16 bit. Then we have another 8 bit for the high and low humidity, and then the checksum. And then finally we have data validation functions. So actually these functions verify the accuracy of received data. Ada data received is or transmitted in error or without error. So we use the checksum. For the DST11, we use checksum from the data and comparing it with the checksum provided by the DST11. So we have one checksum that generated by the DST11. Then we do another check, generate the checksum too from the data received and compare it. Right? Whenever we add that two checksum, actually we got 0. So the answer correct. Right? The data is no error. And then writing and testing the software in stepwise manner with for the works that related to the complete system. So first we need to combine the software developed earlier and the DST11 sensors and to C base 2x16 LCD drivers into a unified system. Initialize both of the DST11 sensor and I2C LCD to ensure proper functionality, and to wait loop until the process time out or the system is necessary to process. Retrieve the temperature and humidity data from the DST11 sensor. Verify that received data is error-free. If an error is detected, indicate a system error and re-enter the wait loop until time out occur. That means we jump back. Jump back here. And then retrieve again the temperature, check again if the error free or not. Eh? If not, again, if error again jump back, until it is correct, then process and format the temperature and humidity data to match the LCD requirement. Finally, display the formatted temperature and humidity data on the LCD following the agreed format, and then re-enter the wait loop until the time out occurs. So finally, after the complete software development and system integration, or software integration, sometimes we call it, right? We jump into the final stage, which is a system test. Right? The final test phase evaluate the integration of both hardware and software components to ensure they meet the defined functional specifications. Which in the definition stage, the tests are connected as follows, right? Refer back to the what? The I think here. Wait. I think it's here. Yeah, functional specifications here, and the per state. Okay, then sorry. First, we check the data update rate, verify that the display updates every 100 milliseconds, ensuring real-time representation of temperature and humidity values. Then LCD display layout. Line 1, check that the temperature is displayed in the format temperature XX per degree Celsius, where XX represents the measured temperature value. Confirm that the humidity is displayed in the format hum XX% indicate the measured, XX indicates the measured humidity value, and timer configuration validate that the timer is properly configured to trigger data reading and display updates precisely at 100 millisecond interval. In the system later, we can use a stick timer, right? Stick timer, which is working at 100 millisecond interval. So at each 100 milliseconds interval, that stick timer will trigger the processor to read data and update the LCD. So this final testing ensure that the system performs as designed, meeting all specifications for accuracy, response time, and usability. Right? Any issues identified during this phase are addressed and resolved to guarantee a fully functional system. So that's all about it. Right? That's all about the project developments. And here's the references that I use. Right? Bawano, Jonathan, K. J. Ayala, R. H. Bennett, L. Coates, and C. Coach. B. Bray, Microsoft MP Pro, hardware software, deficing applications. Alright, that's all. Bye bye.